So hi, everyone, and welcome to this virtual CEETRON Summit. So my name is Fiona Vinkera, and I will be the host for today's event. So before we get started, I do have some housekeeping items to cover. So first, this CEETRON Digital Summit will be recorded and made available to you later. And next, we'd love to hear from you during the event. So if you have any questions, feel free to post them in the Q&A section below, and we will answer them at the end of this webinar. Concerning the agenda, so our CAE Director of Engineering, Andres Rodriguez Villa, will start with a brief overview of TechSoft 3D, and then have a discussion about simulation and analysis components and workflows. After that, it will be followed by a live demo presented by Isabelle de Galzin, who is our senior consulting engineer. And then we're very pleased to have two of our partners presenting their applications today. So we will be joined by Trevor Laughlin. Actually, I hope I'm not misspelling your name, who is VP of Product at nTop. And then by Egi Mata, who is team lead front-end engineer, and he will be showcasing Optimad demo. So finally, we will have a Q&A session. And as anticipated earlier, we will answer any question you may ask during that section at the end of this webinar. So without any further ado, I'll hand things to you, Andres.
Thank you, Fiona, and thank you all for joining us today. My name is Andres Rodriguez Villa. I oversee the product management and the engineering of TechSoft 3D CA toolkits. Let's start with some introductions. First, a few quick words about TechSoft 3D. Our job is to provide software development toolkits to developers who develop engineering applications. Over more than 25 years, our components have integrated the applications of about 700 partners. It's probably highly unlikely that you have never been confronted to an application where our technology is working behind the scenes. In terms of size, we're about 130 employees distributed worldwide with a strong proportion of engineers, of software engineers, developers. Our HQ is in Bend, Oregon, and our main development offices are here in France, in Lyon and Sofia Antipolis, where Isabelle and I are today. And then in Norway, which is in Tunsberg, which is just south of Oslo. Since 2020, our growth is backed by Battery Ventures. First strategic move there at the time was to invest in the CAE market by acquiring two specialized companies. First one, our Norwegian friends, CEETRON AS, actually not only Norwegian, I was part of that team, and Visual Kinematics as well. So today, with those acquisitions, TechSoft 3D components really offer unique coverage of the CAE space, as I hope to show you today. So that was our part of the introductions. We're going to go ahead with a survey and get some information about yourselves. We're really interested to understand what type of CAE application you're building. There are many types of CAE applications, and here's a list, so please answer the survey. Thank you.
So 10 seconds left to finalize. I see that those still answers. Okay, Andres, I think you can go.
Thanks a lot. Yeah, and all those types of applications really rely on different technologies, and CA is really a big patchwork of technologies. So I'd like to dive a bit deeper into these building blocks that you will find throughout different CAE applications. CAE is a very diverse domain. even more diverse than what I'm presenting here. And we're focusing on a finite element-based CAE in this presentation. And it involves many different technologies. Building such applications is really not an easy task. So we require a wide variety of skills. You need software engineers, of course, but also experts in geometry and physics and modeling, numerical methods, math, visualization. That's what makes CAE so exciting, by the way, but it also makes it an ideal candidate to use third-party components when you're building an application. One good way of looking at all these technologies is to look at what I call the standard workflow. This is a workflow that you will find in a solver-centric application. And it goes very easily from a setup of a simulation to its resolution, its computation, and then the post-processing side. In the setup stage, it's all about providing all the data necessary for the solver. A big chunk of this data is the geometry. And that's where you have a few technologies here lined up, importing CAD files. Of course, some applications still use STL, but it's highly preferable to access the CAD definition. So being able to read different native formats is interesting. That CAD representation to get into finite element world has to be transformed into a mesh. To do that, the process will rely on the tessellation of the BREP. More often than not, those tessellations are not completely compliant. A mesher imposes some constraints on a tessellation for it to work. It's a pretty well-defined mathematical object. So tessellations should not have any self-intersections, should be watertight, and strictly speaking, should be manifold. So there's all this, it seems like a little step, but the CAD tessellation repair or mesh healing is a time-consuming one. So having some technology there to help out, to automate is quite important. Once the tessellation is compliant, then you can feed that into a mesher. The mesher will produce a finite element mesh with the desired mesh size, with looking at some control on the mesh quality, the element quality, and also at the geometric precision. You don't really want to change the initial design geometry too much, or at least you want to have some control on it. That's a big part of the setup. Of course, you're going to be adding initial conditions, boundary conditions, solver parameters, anything that the solver needs to start running. That's fed into the solver. The solver does its job. There's a lot of things in the solver, of course, talking about physical modeling, numerical methods. At the end of the day, there's linear algebra. We're always going to be solving some sort of linear equation or an eigen problem in structural analysis. The solver does its job of predicting and spits out a lot of results, very large data sets, gigabytes, hundreds of gigabytes. This is raw data. There's still some work to do. Mechanical engineers will dig into that data, perform analysis or post-processing. Can name it both ways, I guess. And they will, extract meaningful data of those very large data sets. Once they do that, it ends up in some sort of report, or at least that data needs to be shared with all the stakeholders in order to understand what the simulation is trying to answer. So that's the main flow: 1, 2, 3, set up, compute, analyze, and share. There are other technologies that are involved at different steps. Visualization, of course, that's all over the place. You're going to want to follow that object visually in most cases. CAE import and export. Well, that can be handy in some situations. For example, if you're chaining two different solvers, say you've done an injection molding simulation and you want to do some structural analysis on the injected part, well, you might need to export it into a given format for the structural analysis code to be able to work on that part. Another use case here is for applications that are not solver-centric. Good example, nTop, for example, and the optimization algorithm feeds on CAE or on simulation results, and in that sense needs to be able to import various types of formats. And finally, automation. That's sort of a generic technology that any engineer likes to have whenever something can be scripted. and done automatically, well, it's a nice thing to have. So yeah, in summary, there's 8 different technologies here to build a full solver-centric application. Even more if you look at what's happening into the solver. So the question is, what is the cost of developing every component? If you're starting from scratch, do you really want to develop all these 8 different blocks by yourself? Well, first of all, you need to set up a very wide, multi-talented team. Then you have to spend some time. Well, I think it's quite obvious that the question of the buy or build question, the idea of going for component-based development is really well adapted to the CAE space because of this wide variety of technologies. Buy or build, well, there's benefits, there's drawbacks. As anything in life, it's a trade-off. On the benefit side, for me, the most important benefit is to be able to optimize your resources. If you're starting a new application, you probably have some sort of core specialty, some core know-how that you really want to invest in. If you have this brand new solver with a great new method, you don't want to spend time building a new visualization engine, let's say, for example. So optimizing resources and making the most of the talent you have is one of the benefits. Second benefit is that if you use a component, that component is going to be used in other applications, of course. It's going to be much more exposed than anything you can develop in-house. It's going to be more diversely exposed. So at the end of the day, the component will, by definition, by construction, have a better quality, basically, because there will be more feedback on that piece of software. And finally, the obvious benefit, the cost. Yeah, if you want to build a rendering engine, well, it's 10 to 15 engineering years. Do you really want to pay for that? Time to market is quite obvious. You can take it off the shelf instead of waiting that time to have that component. Of course, that comes with drawbacks. It's not your IP, it's not your software, so you have reduced control in what goes into it. Synchronizing releases can be an issue too, and that's really where the difference in between component providers is. You really have to choose your right strategic technical partner, the one who will allow you to have as much control as possible on the content of the component and be listening to you and trying to synchronize as much as possible the releases. Now, in terms of what TechSoft 3D offers behind all this, well, obviously we have a lot of solutions here for different types of technologies. The products line up as this slide shows. For CAD import, Hoops Exchange will allow you to read 30 plus different formats and produce tessellations. Polygonica is there for the mesh healing, repairing the tessellations. It also has some nice features such as Boolean operations or defeaturing, which come in handy in certain CAE use cases. Could be injection molding. If you have the mold and you want to add some runners, well, then Boolean operations on meshes are quite cool. CEETRON Mesh does the meshing, 2D, 3D meshing. There's quite a few meshes. The most popular ones are those surface mesh for triangles and quads, and volume mesh for tets, and possibly some pyramids if there's quads on the surface. CEETRON Solve, well, CEETRON Solve can be seen in 2 ways. If your application is not solver-centric, you can use CEETRON Solve as an integrated FEA solver, providing data for your application. If you are solver-centric, you might want to have a look at the linear algebra that's in there. We have our own IP on that, providing a direct solver, 2 varieties of iterative solvers, and 3 varieties of eigensolvers. As any solver, it's really about performance. The only thing I can say here is that it might be worth benchmarking at some point. CEETRON Envision. CEETRON Envision is a sort of massive framework. Vision, of course, there's visualization there. So it is a visualization engine, both on desktop and web. But it's not only that. It's tailored for CAE, so it's very efficient in terms of rendering, but it also does all the data handling and the data processing, data extraction. All those big, large data sets require some special care to pull out the data efficiently and to perform the extractions that are necessary for the analysis tools. Examples are the cutting planes, animations, plots, ISO surfaces, all the post-processing tools are built in with CEETRON Envision. Finally, all the feature set is available in Python. That's the automation side. You can automate post-processing with CEETRON Envision. And finally, CEETRON Access, sort of the CAE twin of Hoops Exchange, reading and writing, 30 plus formats, standards, Nastran, OpenFOAM, Fluent, ANSYS, et cetera, Bacchus. For those who are our partners, I wanted to give a bit of insight of what's new. We have now released a Hoops Exchange bridge in between with CEETRON Envision. This allows to bring in CAD models alongside CAE models within the same view, extending the capabilities of Envision for pre-processing. We're going to be releasing operators within the next few weeks. These are operators allowed to develop custom UI interactions within a view. So anything that has to do with the keyboard or the mouse, you can develop your own type of user interaction embedded in the view. In terms of meshing, next week we will do the official release of the parallel version of the surface mesher. We've implemented a divide and conquer approach. Our first feedback is talking about 10 times speed up on 16 cores. And we'll continue down that line further this year. In terms of CEETRON Access, we're setting up a plugin framework. We want to promote CEETRON Access more as a universal finite element data structure than as a catalog of readers. Of course, the readers are available, but this will allow to implement custom readers and allow for third-party contributions to hop on the wagon of this universal model. Finally, what can you expect further on this year? We're going to continue enhancing the pre-processing support in Envision, introducing CAD to mesh mappings. This will allow to impose defined boundary conditions directly on the CAD, for example. We're going to be introducing specific visualizations of structural elements and FEA boundary conditions, make things more FEA specific. CEETRON Solve will be having a hard look at preconditioning on hex mesh matrix structures. That is the use case. We're a bit behind competition, so we're going to be optimizing that as much as possible. CEETRON Access, I think this will be in Q3. We'll have an official support for formats within the ANSYS data processing framework. There will have an ANSYS mechanical and Elastina extended support and ANSYS motion as well. And in Q2, we'll be adding the VTU format from VTK to CEETRON Access. With that, and before we go on to the demo, we have another survey. Now we'd like to know what industry you're working in and actually what your end users are working in. What industry do you serve? Please let us know.
Okay, Isabel, up to you.
Thank you, Fiona. So this demo is going to showcase a complete CAE workflow that can be covered with TechSoft 3D products. So basically, all the visualizations that you are going to see into this demo is performed by CEETRON Envision. So first, I'm going to load a Katia V5 assembly file, which is an aqua bottle. So this loading is performed by Hoops Exchange, who is able to tessellate the brep, read into the CAD file, or also to read directly the tessellation stored in the CAD file. Today, we are going to work specifically on the body of the aqua bottle. So here we are on a medium tessellation level, but everything can be customized. We have different kind of tessellation. Normal one, I would say standard, accurate, grid-aligned tessellation. So we are going first to tessellate the body of the bottle. So this is the tessellation generated by OOPS Exchange. And unfortunately, sometimes this tessellation is not directly usable by a mesher. So it needs to be repaired because to be used by CEETRON mesh, the tessellation must be watertight, must be manifold, and mustn't contain any self-intersection. So behind the scene, Polygonica is used to repair the mesh. And then we can give this tessellation to the mesher to generate either a 2D or a 3D mesh. So here we are going to generate a 3D mesh. Of course, a lot of parameters are available, but we are keeping just this one exposed here. And we are going to generate a mesh. So when the parallel meshing will be available in the next version, it will be much more quicker. So here you can see that we have a very refined mesh, especially on the bottom of the part. So for you can see here, it's of course a 3D mesh. So you can see here that it's a 3D mesh, even if it's not easy to see it on an empty thing. And we are going to move now to the next step, which is giving this mesh to the solver. So we are going to simulate the fact that I will take this bottle in my hand. So I will place my fingers at the right place, designed for that. So the thumb here, and the other fingers there. And we are going to apply a force of 10 Newton, which is largely enough. Pick some restraints to say, okay, there are some parts that doesn't have to move. So the bottom of the bottle and maybe the top here. It is good. We are going to say that this bottle is made of high density polyethylene, and we are going to give it to the solver. So here, CEETRON Solve is calculating the results, which are displayed by CEETRON Envision. You can see a lot of scalar results, vector results. So for example, the displacement here, or the external, applied force, which are, of course, inside the bottle. We can show the displacement with the displacement scale and generate an animation. I'm going to remove all the vectors inside. And if you want to share your result with everyone, you can send it to the cloud. Open this link, and you have exactly the same thing. And if you have your cell phone, I invite you to scan this QR code, and you will get exactly the same results on your phone.
Thanks,
you.
Isabel.
Thank you.
Thanks a lot. So now we will have Trevor Laughlin from nTop, who will be presenting nTop company.
Thank you very much. Let me share my screen here. Okay, well, thank you everyone for being here. I'm excited to be here. But like I said, my name's Trevor Laughlin. I'm the VP of product here at nTop. So three brief topics today. I want to share a little bit about nTop, what we do, why we do it, just to give you some sense of the context in which the TechSoft CEETRON components are used in our application, and a little bit about why we chose the CEETRON components at the time. A little bit of background on that, and then a few application examples at the end, just going to show how it manifests in the software for some design applications. So at a very high level, mission at nTop is to develop powerful computational design tools that enable creators to accelerate innovation and deliver products the world needs. And so our focus and what you'll see at nTop is really looking for kind of like breakthrough design opportunities where there's really places where engineers are trying to design parts that they couldn't before, or trying to design parts in ways they couldn't before. And those are the kinds of, that's not every part in the world, but there's a class of parts where those opportunities exist. And that's the kind of, that's where we focus at nTop. So back in 2015, when the company was starting, we realized that engineers have this complexity problem. And what we mean by that is, around this time, additive manufacturing was kind of picking back up, especially in metals. And that really opened up a whole new design space that wasn't before available. And what we found was the tools at that time weren't allowing engineers to tap into that design freedom. And so we wanted to, we first set out to solve that problem. So an example here on the left, this is an additively manufactured heat exchanger. You can see this is it's been cut in half down the middle, but you can see this complex infill pattern that's used in this type of heat exchanger. And so what that does is it dramatically increases the surface area, so you can get a much better heat transfer performance in a very compact space. But designing that level of complexity in CAD programs at the time was very painful and slow, if sometimes in some cases not even possible. So this is kind of where we got our start working on these kinds of very advanced parts. I'll give you one example that really was kind of an eye-opening experience for me in my early days of nTop. I think it was early 2019. We were visiting a customer, I think it was GE Aviation, and in the morning they took us through their current design process for a part that looked very similar to this in terms of complexity. And they were using their existing CAD program to do it. And what they had to do was they couldn't model the part in one CAD instance. They had to actually break it into 12 different submodels, take each one of those submodels to 12 different workstations with 12 different instances of CAD running, have all the parametric models set up the right way, punch in the numbers there, and then if all those models, generated or regenerated, slice them all separately and hope that it all came together at the very end when you kind of combined all the slices back together to get it manufactured. And so doing all of that for them at that time took about 1 week just to get through that submodeling and putting it all back together. And so that was the morning session. We went out to lunch. We came back in the afternoon and we sat down with that part in nTop. In about an hour, we recreated that workflow for them in nTop. And at that point, they basically had real-time iterations that they could work on that part. So that was kind of, back in 2019. And we thought, okay, this is where we want to get, more people to that point where you can design and iterate that fast. So to do that, there's really three core technology components that nTop is built on. So first is implicit modeling, which is a SDF or signed distance field based approach to how we define geometry. So in a traditional CAD system, there's explicit faces and edges and all of that. With implicit modeling, we're defining the geometry basically through mathematical equations. So shapes are defined mathematically, modeling operations like Booleans and offsets are all defined mathematically. And that's really what gives implicit modeling its speed and reliability and all the complexity that it can do from a modeling perspective. The second is what we call field-driven design. So what we found was with implicit modeling, you can essentially think of it as there's so much geometric freedom, you can almost optimize every point in space, especially with additive manufacturing. And that's, on one hand, might sound amazing. On the other hand, it could kind of be difficult to comprehend, like, okay, how do I actually do that? And so we kind of came up with this concept we called field-driven design. And really what that is if you think of a lot of engineering quantities of interest, stress or deflection, those are naturally defined as 3D fields, the same way our geometry is. And so we came up with ways to basically overlay 3D data, whether that's from simulation data or physical test data or whatever it is, kind of directly connect that to the geometry so that you can modify and optimize the geometry in ways that you couldn't any other way. So this illustrative example in the bike seat, what you're seeing there is, the green where these kind of lattice beams are placed. We didn't go in there and manually model every one of those beams and where they want to be bigger and smaller. We basically built a computational model that says, hey, where, given these rules, where the deflection is high, which is that contour plot you're seeing in the background, put more beams there. And then the software just automatically kind of, takes that field, that deflection field as input, and will output the geometry according to that model that you set up and do that automatically without having to manually think about it or model it. The last piece is kind of the computational framework that brings it all together. So we kind of refer to this as design automation. So in nTop, it's a much more algorithmic approach, much almost like visual programming to a degree, but that's very different than kind of the manual drawing you might do in a CAD system. But this computational approach and framework is really what ties everything together. And once you have a computational model built, makes it very, very fast to iterate in nTop. And so what that means is, and this is kind of a simple schematic of that customer story from earlier, today a customer might sit down and get through 3 or 4 iterations in some amount of time. And with nTop, it might be the case that building that first model might feel like it takes a little bit longer. But once you have that computational model built, that's kind of where the magic happens, and you can iterate very, very quickly, go through more designs in the same or less amount of time. And that was basically that example I gave from GE Aviation. This is kind of their experience in a simple schematic. So last slide about nTop, just to kind of give you a sense of the type of applications we focus on. So we have 6 main applications here. So lightweighting is really, reducing material as much as possible to make as light as parts as you can. Thermal management, we saw the heat exchanger example earlier. Fluid management, this is kind of optimizing fluid flow in certain applications like manifolds. Mass customization, we get a lot of use there in the medical industry for like patient-specific devices. And the last 2 are really kind of this energy absorption and then acoustic vibration. It's like ways to generate geometry to kind of tune certain responses of parts in a way. So if you want a certain part that feels a certain way or responds to an impact a certain way, there's different ways to kind of connect those physics with the geometry and create some shapes that kind of tune to the desired response. So backing up a little bit, 2018. I had actually just joined nTop. This is how we started. This is kind of how I started. This is my personal story at nTop. So I had started early 2018. I was an application engineer. A few months in, before that I was in the aerospace industry doing a lot of FEA structural optimization. So I was familiar with those types of tools. A few months into nTop, the person running the product team at the time asked me if I wanted to join as a product manager, kind of start to build in some simulation capabilities in the product. And I said, sure, that sounds great. Like, what's that? What am I supposed to do? So the challenge I was kind of put in front of me was, okay, we want to launch nTop basically 1.0 a few months from now. We want to have integrated simulation. That's like, a key component of our MVP. And, that's your job, figure it out. And so, okay, went through the whole build by partner sort of exercise, thinking about it. And at the time we knew that there was like 3 things that were really important to us that we were looking for. One was, so you might expect, we needed to, do something that was relatively quick to develop, and we had a very small team to do it in a short amount of time to do it in. The other part was, with nTop, we have simulation tools built in, but we're not a validation tool, right? We're not saying, hey, use nTop to do your CE validation for something else. It's providing simulation tools in nTop so that it's more accessible to do those kinds of analyses in the loop. So we wanted something that's fast, but we also know that our customers, who are engineers, they need to trust their tools. So we're trying to find that right balance of speed and accuracy and reliability. And the last piece was nTop is usually deployed in a way where it's working side by side with CAD and it's working side by side with existing simulation tools. And so we knew that really seamless interoperability with kind of the existing CE tool suite was important. So these were the kind of three things that we were looking to check the box when we started. And we went through, did we build this in-house? Do we look at different open source tools? We, eventually obviously landed on CEETRON, and we felt like that was those components checked all those boxes for us. So flash forward to today, what's it look like in nTop today, just from a capability perspective? We have a pretty decent suite of like integrated structural and thermal FEA capabilities, and that's where a lot of the CEETRON mesh and CEETRON solve components are used. In the middle here, we'll look at this in just a little bit more detail in a minute, but really a different set of tools for geometry optimization, and a lot of that is running off of the CEETRON solve component. And one thing I'll mention here is, for us, we wanted to focus on the geometry, the optimization, that layer. We didn't want to focus on the solver technology. But what we found, and I think what we appreciated, was the APIs were very open in that it gave us enough access to very low level control that it allowed us to build kind of our optimization framework on top of it in a way that we thought was best. So from a development perspective, we appreciated that level of control working with the APIs and these components. And then last, being able to build out a pretty broad suite of interoperability between a lot of the different tools that our customers use alongside nTop, ANSYS, Hexagon, or Nastran products, CGNS for a lot of fluid flow applications, and Abacus is another example for some of the structural and especially nonlinear applications that we sometimes find our customers working on. So a couple examples. So this was a kind of a structural optimization case. This is for a 3D printed bracket. It was a part on a NASA satellite. It's one of the brackets holding a couple of things together. And so the general flow that you're seeing here is you bring in your baseline design, kind of your design space. We do the meshing in nTop. CEETRON mesh is obviously used there. The next step, and there's a lot happening here, but I'll just summarize it in one image, is doing this technique we call field optimization. So there's two things happening here. One is it's kind of doing an initial global topology optimization to find that initial course shape. And then in addition, since it's 3D printed, this part has a very complicated infill. And then the next stage is what we called field optimization, which is basically going in and for every part of that infill, every wall thickness, every shell, all the shell thicknesses around the boundary of the part, it's optimizing every bit of that as much as it can down to the manufacturing tolerance. So if you look really closely, you'll see varying wall thickness around the boundaries and throughout the infill. And all of that optimization and geometry techniques is what we've built on top of the CEETRON solve components that we've been using. And then last, usually the next step is after you've done your optimization and design in nTop, there's always that validation step that our customers do. And this was just an example of taking a mesh that we generated in nTop, exporting it out from directly to Abacus in this case, and just importing it, and you have everything right there to do your validation step. Last example, this is kind of an interesting case where we had a customer who is actually a microbrewery. And so they stick a device down into the tanks and spray fluid out of it to do the tank cleaning. And their initial device on the left-hand side here, it didn't have like a uniform spray outlet. And so it took longer and it took more material to clean the tanks. And what they wanted to do was kind of optimize that shape so that they had a more uniform flow from that device so that it would clean the tank faster and better. So in this case, we weren't, it was a little bit different configuration, I suppose, of how nTop was used, where the initial design came in, we would actually mesh and export that and connect with ANSYS Fluent to run a CFD analysis, import those results back into nTop, and through some clever ways of thinking about how to shape geometry from the fluid flow results, you can kind of update the geometry, and you do that loop a few times. And after about 5 iterations, you come out with a shape on the right-hand side that is the geometry has been reshaped, and the end result is the flow is much more uniform like they wanted. So in this case, we weren't running the analysis inside of nTop, but the CEETRON mesh with the pre-processing, CEETRON access with the interoperability to and from ANSYS Fluent kind of helped us close that loop and make this iteration possible inside of nTop. So that was my last slide. I appreciate the time and happy to field any questions at the end if there's time for it.
Thank you, Trevor. Thanks a lot for this presentation, and especially having and diving into CEETRON mesh, solve, as well as access. Seeing how our partners are using it, it's always really great. And now, Egi, it will be your turn to present and showcase your application using CEETRON and Vision.
Great, thank you. Thanks for all of this, for inviting me in this webinar. I will share my screen a bit. Okay, I'm going to share my entire screen because I have to showcase a demo of the project in a bit. Okay. Okay, so I'm Egi Mata. I'm the front-end team lead front-end engineer in Optimad. Optimad is independent software software house which with more than 15 years of experience in this field. It was founded in 2006, and it supports international companies for engineering analysis and optimization, and develops softwares for aerodynamic analysis and computational fluid dynamics. The company has designed and developed mainly three main softwares in-house with the aim of automating simulation processes to simplify the business workflows and reduce time. One of these softwares that we're going to talk about now is Mimic. It's called Mimic. Mimic basically is an advanced geometry parameterization and mesh morphing tool for complex design projects. And Mimic works in a block diagram. It's a block diagram software, and it works in a node editor area in which you build multiple blocks together, whereas each block has one scope, and combining all these blocks together, creating the functionalities, you get the desired result on mesh morphing on the models. To show these models, we basically use CEETRON and Vision for Web. Before we go to that, I will just present a backstory on Mimic. Mimic used to be, 3 years ago, Mimic used to be just a backend engine, and it used to be controlled through the terminal. And it used to take a long time sometimes to build an entire workflow in order to perform an optimization or a deformation on a mesh. And nearly 2 years ago, we started to develop the graphical user interface, and it was a really big success for us, because this job that we had to do in order to build all the blocks and the workflows for mesh morphing or deformations, which took around like a job that could take like 1 hour. Now with the graphical user interface, we do it in 10 minutes or less than 10 minutes. And this is a freeform deformation. Mimic does this. Let's say that we have imported, using one of our blocks, a plane, and we use CEETRON and Vision to display this plane. And we use also, in order to transfer or communicate the geometry data from the front end, the graphical user interface, with the engine, which is the backend, we use the CEETRON Data Provider plugin, which is a plugin that is used to transfer all the geometry data, whether the geometry data may be huge in size or not. And it's pretty fast on that side. These are just parameterization deformations that are done on wind turbines, for example. And we can use Mimic in order to specify these parameters of creating a lattice around a part or a whole object, and we deform this object based on the parameterization of the lattices. And here we are using basically an RBF parameterization. We have identified on the wing of a plane, we have identified the vertices of where we want to do this deformation, and based on the parameters that are done in each of Mimic blocks, we perform the deformation. In order to get a better look at this, I'm going to present quickly the software. So for the sake of time, I have already created the workflow here. It took me at least 5 to 10 minutes to create this really small workflow. So as I said before, Mimic works on blocks, and each of these blocks is contained into this node editor area, and each of these blocks has a specific function. For example, the geometry reader reads a geometry based on the file path, it connects with the data provider plugin, and then the data provider plugin connects back with the CEETRON server, which gives us the visualization in the front end. Everything here is connected. Every block here does a specific operation, such as the polyline extractor. It extracts we use Mimic picking environments, creating picking environments made only for extracting a polyline. For example, if we enter this environment, we will see here that we have the 3D scene. Basically, this is CEETRON, and we have selected a line around this sphere, which has 4 parts, as we can see from the colors. And okay, since I have already done this, I'm not going to save the changes. So upon executing this whole workflow, we get the new data, and we will get the result of the deformation here. Basically, this is the new deformed mesh coming from the selected polyline on the sphere. And we can see also a result on this part by selecting points, displaying the deformed geometry as points, and we can see both of the geometry, the original geometry, which is the sphere, the not deformed sphere, and the deformed sphere, which is kind of like the shape of a duck face. And this is one of the most used cases in Mimic, but there are a lot more, and it involves performing and creating more complex workflows using the node editor diagram. And Mimic has around 150 blocks, and each of them performs a different operation, such as parametrizations, freeform deformations, such as this one, either using a lattice, either using an RBF. And also Mimic can do node extracting, can do elements extracting, such as when we have a mesh, a 3D model in the scene, and we want to, or let's say we have a car and we want to split the tire into 2 different parts. We have a specific block for that, which is splits the tire into 2 parts if the user needs to do some modifications on one of the parts of the tires, let's say. And shortly, this was Mimic. I have no other. Okay, thank you.
Thank you, Egi. Thanks a lot. So without any further ado, that will be our Q&A session. So I think we have a first question, which is, if I remember well, it was while Isabel, you were demoing. So is there any way to handle non-manifold surface mesh?
Yeah, thank you for that question. I was a bit cryptic while describing the requirements for a mesher. Of course, yeah, non-manifold geometry can be sort of converted in many manifold geometries, and there is an option there for in CEETRON Mesh. You have to toggle it on. You also have options for CEETRON Mesh to detect automatically the internal surfaces and create back-to-back triangles. So both sides of the volume can be fed to the volume mesher. So answer is yes, basically.
Okay. I think we have a second one, which is more for nTop. So you, Trevor. So nTop is a desktop application. Do you have any plans to take it to the web at some point in time?
No plans as of yet. It's always something we're assessing. There's a lot of good reasons that we could make good use of the cloud, especially around the compute area. So no definitive plans yet, but it's certainly something that we're assessing where it can be useful.
Okay. I have some people raising their hands. I will answer first the question in the chat, and then I will give you the ability to speak if we still have time. So another question for nTop. Again, could nTop explain a little bit about how they represent geometry for both implicit and field-based representation?
Yeah, so maybe a few examples. One, if you know, a lot of our geometry, our implicit geometry in nTop, if you look up, you know, the equation of a sphere and you have, you know, a function that's basically a function of XYZ, and given an XYZ point, you can know the distance to the surface of that sphere. And as long as you can compute the distance from any point in space to kind of where the surface is or the boundary is of the object, where the sign basically switches from positive to negative, you can represent a 3D shape in that way. So that's basically what implicit modeling is doing. And on the field side, if you take something like a stress field, which is just 3D data in space. So again, you have points in space, you just happen to have data associated with them. It's not a distance value, but it's a stress value. And so there's ways to, you know, basically make that a field, and then you evaluate that field just like you do implicit geometry, but instead of getting a distance back, you get a field value back. And you kind of you can tie all those things together in creative ways.
Okay. A question for you, Egi. So Optimad seems to use two-way communication with the server with Envision, updating the full model once your algorithm has computed the deformation. Have you seen any performance issues in this process?
Well, no. Basically, we use two-way communication. We send the request from the front end to the data provider directly, and the data provider is located, is embedded inside the core engine itself. And since this communication between these two is really fast, the data provider will immediately, upon the request send the data back to the CEETRON server, and the visualization is really fast. Well, depending on the model, if the model is really big in size or has lots of triangles, it could take some time, and depending, of course, on your machine. But once the model is fully loaded in the front end from the server, it is really fast, and we can visualize everything without having any performance issues. That is, of course, depending on the model itself and depending on the machine that you are performing these operations, of course.
Thank you, Egi. Another question for nTop. So nTop and CEETRON, can implicit surfaces directly rendered with CEETRON, or they have to be tessellated before?
I think I'll take that one.
Okay.
nTop does not use CEETRON Envision, so that's sort of removing the nTop input here. But the question is, does CEETRON support directly implicit surfaces? The answer is no. CEETRON Envision comes with various data models for unstructured grids, especially on the web, very specific models to optimize that. And it also provides a geometry model, but they're all tessellation based at this point in time, of course.
Thank you, Andres. Visual programming is clearly becoming more popular. What is TechSoft really doing to support this in its toolkits?
It's a good question. Well, beyond providing the functionality that's behind any of those blocks, we are starting to look at possibilities of exposing the API to be able to make those type of applications easier to program. I'm not an expert here. I think it's already possible, but some sort of introspection would be interesting, I think. Again, I'm a bit out of the zone of comfort here.
Okay. Now the question, how would CEETRON visualize launch time series when rendering locally in the client web browsers? Is there a caching mechanism available out of the box, or each step will have to be sent to the client?
CEETRON Envision comes with all the data processing, so I suppose here we're talking about an animation. The animation is generated on the server side, and it's the entire display model that corresponds to the animation that's being streamed progressively back to the server. So yes, there will be a bit of lag there as each frame comes in. The server is chugging out different frames. But once the full animation has been computed and streamed, then everything is residing in the client, and you get desktop-like user experience, basically. And there is a caching mechanism out of the box, of course.
There is a question from Max. How about structured data, voxel meshes, or point clouds?
That is a very popular question for a product manager, especially the structured data. Point clouds, we don't get that much in the Envision environment, but structured data, we do have a 2D structured grid model, which is used by one partner in a very specific one, but we are getting more and more requests. So this is something we're looking at to put on the roadmap. Maybe not this year, but it's sort of on the top of my list for 2025.
Oh, I think I missed this one. Does CEETRON Mesh only accept tessellation data as input, or there are any capabilities of surface, volume mesh adaptation? Thanks.
First answer is yes, it's only tessellations, and although it has some built-in repair capabilities like eating up holes and removing very small edges, we tend to recommend to use a valid mesh as input for the surface remeshing, actually. In terms of adaptation, well, there's mesh size control that can be connected to any way of computing. We do have behind the scenes, I think we do have some sort of error estimation, but I'm not promoting that until we have a full grip on it. But if you do have your own error estimation algorithm, and which produces a mesh size, you can impose your own mesh size. There's a callback mechanism there.
We don't have any other questions, so if you still have questions, now is the time to put them in the Q&A sections. And otherwise, I'd like to thank everyone for joining us today. As I said at the beginning, it has been recorded and it will be shared and made available to you after this event, probably tomorrow. So again, thanks to Andres, Isabel, Trevor, and Egi for joining today, as well as all of you. And at the conclusion of this event, there will be a quick survey. If you have time to take it, feel free. It will help us to make sure to improve our content for next time. And thank you all for today. Have a great day.
Thanks a lot. Bye, guys.
Bye, everyone.
Bye, everyone.
Thank you. Bye.